Question number 1. In an ideal transformer, if K is some constant, then supply voltage V in terms of its magnetizing current Im can be expressed as option A jkf Im, option B minus jkf by Im, option C minus jkf Im, option D minus jkf by Im. So here this is Im is the magnetizing current, and this one is the I have made here the equivalent circuit of a transformer, and we have to write V, that is terminal voltage, in terms of Im. So we can neglect this one, and we can write this one V1 prime in terms of Im. So what will be this one? This will be simply V1 is equal to Im into Jxm, that is inductive reactance into the current through it. So this will be inductive reactance can be represented 2 pi fl. So here I can collect K to be 2 pi lm, 2 pi and lm, so that it will be a constant and we can represent as given in the question. So this will be jkf Im. So here option 1 is the option 1 or option A is the correct answer. Next question is, a 400 by 200 volt 50 Hz transformer operates at a flux density of 1.2 Tesla when energized from its HV side. For this transformer, linear dimension of the core are doubled. So for this transformer, linear dimensions of the core are doubled while the number of turns are halved. So here two informations, one is linear dimension of the core are doubled and second is number of turns are halved on both sides. If the transformer is now connected to 800 volt 50 Hz on its HV side, then its flux density would be. So this is the question and options are given to be option A 0.6 Tesla, option B 1.2 Tesla, option C 3.6 Tesla and option D 4.8 Tesla. So let's have the solution. So the EMF equation of transformer is given as E is equal to 4.44 ANF, and here this one is BANF. B is the flux density, A is the effective area of cross section, N is the number of turns and F is the operating frequency. So here I can represent like that. Suppose we will consider the high voltage side, so we will consider two cases, suppose first case and second case, and in both cases we will consider the high voltage side of the transformer. So EH1, that means first case high voltage side by second case high voltage side, this will be is equal to EH1 by EH2 is equal to 4.44 B1 A1 N1 F1 by 4.44 B2 A2 N2 F2, and here the constant will be cancelled out. As this is given here, F1 is equal to F2, that means 50 Hz. Here also 800 volt 50 Hz and here also given 50 Hz. So frequency is not changing and all other options are changing. So we will cancel out the constant, that is 4.44, and the frequency, and the rest terms are EH1 by EH2 will be equal to B1 A1 N1 by B2 A2 N2. So now we will put the values. So in this question given that first it was operated by 400 volt, now it was operating in 800 volt. So this is 400 by 800 is equal to B1 x2, x is the B1 x square. What is x? X is the linear dimension, and if linear dimension is x, then area will be directly proportional to x, whether it is circular or rectangular or anything. This will be directly proportional to the square of linear dimension, that is area. Area is always directly proportional to square of linear dimension. So B1 x square n by B2 2x square, because linear dimension is doubled. Linear dimension is doubled, 2x whole square, and number of terms are halved. Number of terms are halved. So n by 2. So this will be b1 by 2 b2, and this is 400 by 800. That means half is equal to b1 by 2 b2. So we can find out that b1 is equal to b2. That means what was b1 value? b1 value was 1.2 Tesla. So b2 value will also be the same value, that is 1.2 Tesla. So answer will be option B. Next question, question number 3. The maximum efficiency for a transformer occurs at 80% of full load. The core loss is PC and the ohmic loss is POH. For this transformer, the ratio PC by POH is, that means core loss by ohmic loss is dash. So in this question, first given that maximum efficiency for a transformer occurs at 80% of full load. So we know that ohmic loss, that is the copper loss represents ohmic loss. Ohmic loss at x of full load, x, that is fraction of full load. Fraction of full load is equal to x square into ohmic loss at full load. This is the formula we know. This is the expression we know already. So x square will be this one by this one. So this will be x square is equal to ohmic loss at x of full load by ohmic loss at full load. So at maximum efficiency, x of full load, at maximum efficiency always PC, that is core loss, is equal to copper loss, that is ohmic loss. So I can write here that x square is equal to PC by ohmic loss at full load. This is the formula. So here in this question there is a mistake, that is the second line, the core loss is PC and ohmic loss is POH at full load. There should be mentioned at full load, at full load, at full load. Sorry, at full load. This should be mentioned because the core loss is constant for every load, but the ohmic loss is not constant. At every load change there will be different ohmic loss, so it should be mentioned here. So I can represent x square is equal to PC by POH. So PC by POH will be square of x square, and what is x is given? X is given that 0.80, that is 80% of full load. 0.8 square, that is 0.64. 0.64. Answer is option C. Next question. Question number 4. Two transformers X and Y with identical rating and dimensions have 0.8 mm and 1.2 mm thickness laminations respectively. If RC and XM are the magnetizing branch parameters in the equivalent circuit, then here are the options. So what are given in the question? Two transformers X and Y with identical rating and identical dimensions. Then what is given? X have the thickness lamination of 0.8 and Y have 1.2 mm. That means Y has more thickness of lamination. Then what is given? RC and XM. RC and XM are the magnetizing branch parameters in the equivalent circuit. I have already explained in question number 1 what are the magnetizing branch parameters. RC represents the core loss and XM is the magnetizing current parameter. So what will happen? Here given that relation of X and Y transformer and these things. So I am explaining. So what are the options given? I am reading fast. Option A, RC values in both are likely to be equal, but XM of X is likely to be higher than XM of Y. Next is given option B, XM values in both are likely to be equal, but RC of X is likely to be higher than RC of Y. Option C, XM values in both are likely to be equal, but RC of X is likely to be lower than RC of Y. Option D, RC values in both are equal, likely to be equal, but xm of x is likely to be lower than xm of y. So here are the options. So you will analyze this one. If the lamination thickness increases, what happens? This question asking for this one. If lamination thickness of the transformer core lamination thickness increases, then what happens? This is the question asking here. So lamination is done to reduce eddy current loss. This is the aim of laminating the core. So if laminated core used instead of solid, laminated core used instead of solid, thickness of why we are using lamination? To reduce the eddy current loss. If we use solid core instead of laminated core, what will happen? Eddy current will find its path to flow and it will cause the heat production and it will cause eddy current loss. So to reduce that eddy current loss, we are going for the lamination. So if the thickness of lamination will increase, eddy current will increase, because the current will find more path to flow and it will cause the eddy current loss. So eddy current will increase, that means eddy current increase means loss will increase, eddy current loss will increase. Eddy current loss is a part of core loss. So as core loss increases, that means RC, that is the core loss component, will decrease. Because core loss is increasing, that means core loss resistance will decrease. So this is the one thing we have to consider. So what are the options here? One here is RC of x is likely to be higher than RC of y. This is one option, and here another option. RC of x is likely to be lower than RC of y. So here, as y has higher thickness of lamination, what will happen? RC will be lower. So RC of x will be higher. So this is the correct option. And here given that xm values in both are likely to be equal, not equal, are likely to be equal. So what xm represents? Magnetizing reactance, which is less affected by lamination, because this xm represents the magnetic path. This is the magnetic path, and we are making the core to provide the magnetic path to the flux, not the electrical path. So we have to always eliminate that electric path by laminating the core. So this RC decrease means this will provide more electrical conducting to core, but magnetic permeability or the permeance is still less affected. So here answer is B. Next question is, a single phase transformer has per unit leakage impedance of 0.02 plus j 0.04 ohm. Its regulation of power factor 0.8 lagging and 0.8 leading are respectively. So a single phase transformer is given, and here leakage impedance is given. Leakage impedance in terms of R plus jx. So in terms of, as here per unit is given, so here in the question ohm should not be given, because here given that per unit. So R plus jx is given and both are in per unit. So we know that voltage regulation in terms of per unit voltage regulation is equal to R per unit cos theta 2 plus x per unit sin theta 2, and this will be plus for lagging and minus will be for leading. And what is the theta 2? Theta 2 is the load power factor angle, and here given that 0.8 power factor fast one. For fast, lagging power factor 0.8 cos theta 2 is equal to 0.8. So I have put here 0.8, and R per unit is 0.02 given, plus 0.04 already given here, already given 0.04, and plus 0.6. 0.6 is sin theta 2. Sin theta 2 is 1 minus cos square theta root 2 over. So this will be 0.6. So it will be around, it will be equal to 4%. That means lagging power factor, lagging voltage regulation will be 4%. So what will be the leading voltage regulation? Leading voltage regulation will be only the sign change, that is the minus here. So what will be the answer? Answer will be minus 0.8%, minus 0.8%. So 4 minus 0.8%. Option B is the correct answer. Next question. Question number 6. One transformer has a leakage impedance of 1 plus J4 ohm and 3 plus J11 ohm for its primary and secondary windings respectively. The transformer has HV primary, medium voltage primary, LV primary, LV secondary. So this is the question given. So one thing, this is the leakage reactance form, and R. What is R? R is the Z1. Z1 means this one is primary. R1 means primary, 1 is primary. So here R1 is resistance, winding resistance primary, and this is the inductance of primary, that is inductance or the leakage reactance due to inductive effect of the primary winding. So if the resistance of a primary or secondary coil is high, that means the length of that wire is high. Length of that wire is high. So here in secondary, this one secondary resistance is high. Secondary resistance is high means the secondary coil wire is long, and so that it has more number of turns. So we can say that this one is for HV, this one is for HV, and this one is for LV, low voltage, and this one is for HV. So secondary is high voltage and primary is low voltage. So here option C is the correct answer, low voltage primary. So another thing we should consider here, that here 11 is also given. 11, that means the reactance is also given, and reactance depends upon the number of turns also, because this is the inductance. Inductive reactance is given as 2 pi L, and L is depending upon the N is the number of turns. As here number of turns is also more, we can say that the secondary is high voltage. Next question. In Synchronous Test, on two identical transformers having rated frequency f, option A, both primaries and regulating transformers should be fed from voltage source of frequency f. Option B, both the primaries and regulating transformer may be fed from voltage source at frequencies different from f. Both primaries should be fed from voltage source at frequency f, but regulating transformer may be fed at a frequency different from f. Option D is both primaries may be fed from voltage source at frequency different from f, but regulating transformer should be fed at frequency f. So what are the given here? So long question. So here what is Synchronous test used for? This is for measuring the temperature rise. And what we can do in Synchronous test? Two identical transformers we have to connect, and here we have to connect primary in parallel and secondaries in series opposition manner. And in no load condition. And what is the regulating transformer given? Here is the regulating transformer. We have to provide power or power supply to the secondaries which are connected in series opposition manner. So you have to measure here, connect one wattmeter and second wattmeter here. So this wattmeter will measure the core losses into primaries. So I can make you understand that here primary, What is primary wattmeter is giving? Primary wattmeter is giving 2 into core losses, 2 into core losses, and the secondary transformer, sorry, the secondary wattmeter here, this one secondary wattmeter is giving the 2 into 2 times the full load copper loss, and if we consider the formulas of core loss, both hysteresis loss and eddy current loss are depending upon the frequency. Somehow are depending, eddy current is depending upon the square of frequency, whereas the hysteresis loss is depending upon the 1.6 power of the frequency, depending upon V by F ratio. And I can conclude that core loss is always depending upon the frequency, but copper loss is independent of frequency. So here secondaries are independent of frequency, and primary is depending upon the frequency. So this primary wattmeter reading will always depending upon the frequency. So we can say that here option C, that is both primary should be fed from the voltage source at frequency F, but regulating transformer may be fed at a frequency different from F. So why here given that maybe? Because generally in Synchronous test this is not given from a different frequency source, this is given from this same frequency, same source, same frequency. What is the aim of this test? Test is conducted to measure the temperature rise considering the rated core and copper losses. So to consider the rated parts, we have to always consider the rated frequency of the transformer. So it is mandatory to provide the voltage source of rated frequency to the primaries, but it is not mandatory to provide a voltage source or the variac of same or a rated frequency to the secondaries. Those are connected in series opposition manner. So here option C is the correct answer. Also there is option A, both the primaries and the regulating transformers should be fed from the voltage sources of frequency F. This is also correct, but here what is given? Should be. So this option is not preferred. Here option C is preferred because we can apply different frequency source to the secondaries. So option C here is the perfect answer. Next question number 8. A 3-phase star delta transformer has a secondary to primary turn ratio per phase of 5. Here given that star delta transformer, this one is star and this one is delta, and has a secondary to primary turn ratio per phase is 5. That means 1:5, secondary to primary. So for a primary voltage of 400 volt, the secondary voltage would be, so given that primary voltage is 400 volt, that means this one is a line voltage. Primary voltage is given to be line voltage. So V1L, that means primary line voltage is 400 volt. So what will be the phase voltage? Phase voltage will be 400 by √3 volt. This is the phase voltage. And what will be the secondary? Transformation always occurs in the at the phase manner. So this will be into 5. This will be 5 times that of primary phase voltage. So secondary phase voltage will be 5 into 400 by √3 volt. So this will be 1154.7 volt. And as the secondary is connected in delta, there will be the same phase voltage and line voltage. So V2 line voltage, that means a secondary line voltage will be also the same, that is the 1154.7 volt. Option B is the correct answer. Next is a bank of 3 identical single phase 250 kilovolt ampere 11 kV by 230 volt transformer is used to provide 400 volt low tension supply from a 11 kV 3 phase substation, the effective kVA rating of the bank will be. So here a bank of 3 identical single phase 250 kVA 11 kV by 230 volt transformer used to provide 4 volt low tension supply from 11 kV. So here input is 11 kV and output is 400 volt. That means this connection is delta star connection because the transformers are 11 kV 230 volt and here phase voltage is 11 kV, so, and here line voltage is also 11 kV, and here what is given 230 volt is always the phase voltage, and what will be the line voltage will be 400 volt. 230 into root 3, and this is not the part of question. Part of the question is 3 phase substation. The effective kVA rating of the bank will be simply 3 into kVA rating of single phase transformer. So 3 into 250 kVA, that will be 750 kVA. So VA rating can be calculated from either primary or secondary. So here I have already explained, this one is a delta star connection, and this will be the answer 750. So next question is a 20 kVA 2300 by 230 volt 2 winding transformer is to be used as an auto transformer to give 2300 volt by 2530 volt. Its rating will be, so this one is a 2 winding transformer 2300 by 230, and we will design an auto transformer of rating to 2300 by 2530 volt. So here I am explaining two methods. First one is we have to calculate the K auto, that is the turn ratio of auto transformer, and this is K is always equal to LV by HV, that means it is always less than 1. And what will be K is equal to 2300 by 2530. This one is K, that is auto transformer ratio. And what is the kVA of auto transformer? kVA of auto transformer is equal to, this is formula, 1 by 1 minus K into kVA of 2 winding transformer, from which we are connecting to make it to be an auto transformer. So this will be 1 by 1 minus 2300 by 2530 into 20 kVA. And if we calculate this one, kVA of auto transformer is 220 kVA, and always we connect the transformer in adding properties. In adding means the flux will add together and the voltage will be adding. That means here primary is 2300, secondary is 230. So this will be added to 3052. This will be added, not subtracted. If we subtract this one, the MVA or kVA rating will be decreased. So always we design in additive manner. So this will be 220, that is 220 kVA will be the 220. This will be the rating of the auto transformer. Then what is given? Then also in the options given that conducted, that means conducting kVA. What is it representing? A auto transformer or an auto transformer always transforms power from primary to secondary in two manner. That is, one is inductive like conventional transformer, and another is conducting. That means the auto transformer has always connection between primary and secondary, and conductive kVA is always greater than inductive kVA. And another thing is inductive kVA is same as that of two winding transformer when it is converted to auto transformer. So what is the inductive kVA? Inductive kVA will be same, that is 20 kVA 20 kVA. So what will be the conducting kVA? 220 kVA, 220 kVA, 220 kVA of auto transformer minus 20 kVA of inductive. So what will be the conducting? 200 kVA. Also we can apply the formula. That is K into auto transformer kVA. So what is K? 2300 by 2530 into 220, which will also be equal to 200 kVA. So this is the formula. We are using the formula. So if we don't remember the formula, so what we can do here? So we have to draw the circuit diagram of the transformer, auto transformer. So this is the part, this is the secondary part, which is divided into 2300 and 230, and total it is making to be 2530 volt, and the primary is 2300 volt. And here we have to calculate the currents. So primary current will be kVA rating by voltage. kVA rating is 20k, that is 20 kVA by 2300, which will be nearly equal to 8.7 ampere. This is primary. And secondary current will be, this is for two winding transformer, and secondary current will be 20 kVA by 230 volt, and this will be equal to 87 ampere. So what will be the current directions? Here we will put 87 ampere because windings are already pre-winded, so we cannot change its thickness or anything. So the current rating will be same for the windings, but here the connection will flow more current. That means this will be the addition of two currents, primary and secondary. So this will be 87 plus 8.7. This will be 95.7 ampere will flow here, and one part will flow downward, that is 8.7 in the in the primary part of the auto transformer, and in the secondary it will flow 87 ampere. So what will be the rating? 87 current into voltage, that is 87 into 2530. So rating will be 2530 into 87, or we can also calculate from the primary. That means primary voltage and current are 2300 into 2300 into 95.7. This will also result the same, and this will be 220 kVA, nearly equal to 220 kVA. And when transformer is connected as a auto transformer, kVA transformer with the induction remains the same as I already explained. So here kVA induction will be 220 kVA, and kVA conduction will be 220 minus 20, that is 200 kVA. So here in the options there is no option is given for this one, that is the kVA rating of auto transformer will be 220. So what are the 220 options? Only one, but conducted is given 200. So this is not the option. For this question no option is correct. So what can be changed? Suppose this one is 220 kVA, here we can change this one to be inductively, so that this option will be correct, or we can change this one to be conducted kVA to be 200 kVA. Otherwise this option can be correct. This one here conducted is 200, and here we have to make 220 kVA, so that option C or D may be correct. So for this question there is no option given, no correct option given. Next question is, three single phase transformers are connected to form a three phase transformer bank. The transformers are connected in the following manner. the transformer connection will be. So first thing is that here first one is a star connection and second one is delta connection, and primary we generally consider to be the high voltage side and secondary to be the low voltage side. So first one is capital Y, secondary is small d, that is a delta connection. So we have to here find out the clock angle, that is 0, 1, 6, 11. What is the clock angle here? So I will draw here the draw for the secondary one. For secondary one, here the terminals are A1, B1 and C1, and for primary A2, capital A2, capital B2, capital C2. So capital A2, capital B2 and capital C2, and always the phase sequence is ABC, not ACB. Always here positive sequence. If not anything not given about the phase sequence, then phase sequence always will be the positive phase sequence. So here secondary output terminals are A1, B1 and C1. So how to draw? First we have to, second one is delta connection. So at the middle I will draw this one, a line which represents, and the output will be A1 here, because A2 is the output of primary and A1, small a1 is the output of secondary. So next is, as this one is A1, what will be this one? This one will be A2. This one will be A2, and A2 here is connected to B1. A2 is connected here to B1. So here I can write it to be B1. As I am writing here to be B1, and we will draw like this parallel to this one. So you will like this. This one is B. We will parallelly draw. This will be B1 and this will be B2. This will be B2, and then B2 is connected to C1. So I can write here C1 instead of B2. So as C1 is given here, C1 is the terminal, and I can complete the circuit by this, parallelly connecting this parallelly, and C will be parallel to the primary like this. So this is the circuit of secondary circuit. And if there is a delta in the clock diagrams, we have to consider a virtual ground, virtual neutral. So here is the virtual neutral N, and we have to consider the reference. Suppose here A1 is the reference, high voltage is the reference, this is the secondary, and secondary is leading. This one is suppose A2, capital A2, and this is lagging. This is lagging, and this is always 1 o'clock. This is 1 o'clock. And I want to say here that generally you will find always in every book that A2, capital A2, B2, C2 are the terminals, are the input terminals, and small A2, B2, C2 are load terminals. Never A1, B1, C1 is not used for the terminals in case of notation, but in this question A1, B1, C1 are given to be the terminals. So if we consider this one A2, B2, C2, so answer will be this one, answer will be 11. So here this one is 1 o'clock. So generally in case of all books and everywhere, this is the naming pattern, and suppose this one is the naming pattern, and always one terminal is here connected to the neutral, and this is the input terminals, and in case of this one is the connection terminals, and A2, B2, C2 as the load terminals for the outputs. Suppose this one is given that A2 is connected to B1. I am here connecting this one and this one, and another is like this. So here A2, B2, C2 are given, and how can we draw? First we will draw the primary phasors. This one is An, this one is A1, this one is B1, sorry, A2, B2, C2, A2, B2, and this one is C2. So how we will draw the secondary? Secondary is delta. That means this is Y D, and we don't know the clock. We have to draw this one to know the clock angle and what is the clock structure. So what we have to do? First we have to draw this one. So here terminals is A2. Here terminal is A2, small A2, and now we have to, and as this is A2, this will be A1, and A1 is connected to B2. So I will replace it by B2. And what is B? B is like this. B2. So this will be B1. So this one will be B1, and here B1 is connected to C2. So I will replace this one to be C2, and here I will connect the C. So here A2, B2, C2, and this one is the virtual neutral, and this is also 1. This is also 1. Here output is A2, B2, C2. A2, B2, C2, and connections are different from this one. That is, here A2 is connected to B1, but here A2 is connected to C1. So remember what type of connection. So always learn this connection making or phasor diagram drawing technique, so that you will never fail to answer this type of questions. Next question is, an electromechanical energy conversion device has a cylindrical stator but salient pole rotor. If delta is the angle between the stator field and the rotor field, the average torque developed is proportional to. So here for any electromechanical energy conversion device with a if that one has a cylindrical stator and a salient rotor, so this will be, so this is the common term or common expression. I can write that this is the common expression. This one is the common expression. So this one is the common expression, and this term here can be written to be B sin 2 delta and sin delta, and this term to be written to be A. So here, as this is cylindrical stator and salient pole rotor, this will be A sin delta plus B sin 2 delta. But there are also some cases. Suppose stator is cylindrical and rotor is also cylindrical, then what will be the case? The case will be only this part will be present, and this LQ and LD, that is the direct axis inductance and quadrature axis inductance, there will be no values, and there will be only this one, that is A sin delta. If stator is cylindrical and rotor is salient type, as this is given, A sin delta plus B sin 2 delta, and if stator is cylindrical, rotor is salient type, but excitation current is not given, then what will happen? Here there is a IF term, this will be 0, so only sin 2 delta term will be present, So if both stator and rotor are salient pole, then this will also be A sin 2 delta. So next question number 13. A 3-phase 4-pole alternator has 48 stator slots carrying a three-phase distributed winding. Each coil of the winding is short circuited by one slot pitch. The winding factor is given by. So here slot angle or slot pitch. What is slot angle or slot pitch? This is gamma, and this is given by 180 into number of poles by number of slots. So here given that number of pole is equal to 4. So this will be 180 into 4 by 48. 48 is the number of slots. So this is equal to 15. So slot angle is equal to 15 degree. And what is M? M is equal to slot per pole per phase. That means slots is number of slots is 48 per pole, means by 4 by phase. Phase is 3 phase device. So M will be 4. So distribution factor KD will be sin M gamma by 2 by M sin gamma by 2. So if we apply the formula, what we are getting, KD is equal to sin 4 into 15 by 2 by 4 sin 15 by 2. So this will be equal to 1 by 8 sin 7.5. This is the KD. And what is asking in the question? Winding factor. Winding factor KW is equal to KD, that is distribution factor, into KP, that is pitch factor. So we have to find also the pitch factor. So how can we find out that pitch factor? Alpha is equal to the coding angle. Alpha is the coding angle, and this is here given that short coded here. This is coding CHORDED, coded. Here written that coded. Actually this is coded. Short coded by one slot. That means here alpha is one slot angle. So alpha is equal to gamma is equal to 15 degrees. So KP will be formula is cos alpha by 2. That means cos 15 by 2. That means cos 7.5 degree. So winding factor will be KW, that is KP into KD, which is equal to cos 7.5 by 8 into sin 7.5. So this will be cot 7.5 by 8. Cot 7.5 by 8. Answer is option B. Next is peak value of fundamental component of MMF produced by one n-turn coil carrying a current is. So here we have to consider number of pole is equal to 2, because this is the minimum requirement to produce alternating MMF, rotating alternating MMF. So fundamental component of rectangular wave is rectangular wave is the MMF, and this is given by F1 is equal to 4 by pi into Ni by 2 cos alpha ampere turn. And here what is alpha? Here alpha is the electrical space angle. And what is the maximum value? Maximum value will be occur at 0 or 180 degree, as this one is the cos alpha. So at 0, suppose at 0 peak value will be 4 by pi into Ni by 2. So this will be 2 by pi into Ni. So answer will be 2 by pi into Ni. So where this is from? This question is from electromagnetic energy conversion, and you can find these expressions in also P.S. Bimra, J.B. Gupta, and also other machine books. Next question is, a belt driven cumulatively compound DC generator is driving power to DC mains. If the belt snaps, then the machine will run as a differentially compound motor in same direction. Why this is happening? We can write that always if the belt snaps, then machine. In case of differential compounding, EB by phi, N is directly proportional to EB by phi, and in case of differential compound, phi SH minus phi SE in case of differential compound. And when belt snaps, what will happen? So what will happen here? Suppose this one is the machine having series field, this one is the shunt field, and this one is the armature. So this one is the phi AC, that is series field. This is the phi SS, that is the shunt field. And as this is given, this is a cumulatively compound DC generator. That means phi SS is adding phi AC. That means phi SS plus phi AC is responsible for rotation, for generation of the voltage, and current is flowing this direction. And in case of shunt, in case of shunt winding, this is the current direction ISH. This is the ISE, series field winding. When the belt snaps, that means the mechanical input is hampered, and this is connected to DC mains. So what will happen? What will happen here? This direction will change. Series field direction will change. Series field direction, current direction will change, but shunt field direction will remain same as previous. So what will happen? In previous, that was cumulative. That means phi SH plus phi SE. It was previously. But when belt snaps, phi SH will be same. Because the current direction is the same, but phi AC will be negative. Phi AC will be negative. So this will be differentially compound motor. Differentially compound motor in same direction. Next question, question number 16. The magnetic circuit of a DC shunt generator with negligible armature resistance and bus contact voltage drop remains unsaturated when it delivers full load current at rated terminal voltage. The brushes are kept in the interpolar axis and speed is maintained constant. When the load is switched off, the terminal voltage would be. So here what is given? Magnetic circuit of a DC shunt generator with negligible armature resistance and brush contact voltage. So here given that armature resistance and brush contact voltage drops remain negligible. This one is negligible, and drop remains unsaturated when delivers full load. That means magnetic circuit is somewhat ideal. And then is the brushes are kept in interpolar axis and speed is maintained constant. When the load is switched off, the terminal voltage. And this is a shunt generator, and shunt generator has very good voltage regulation, and this is acting at full load. And this is the external characteristic. This one is the external characteristic for a shunt generator, DC shunt generator. So in this, what is the behavior? The voltage is like this, and this point is the no load voltage. And when we increase the load, this will move like this, and this is the maximum load current. And after that, this load current will start to decrease, and also the voltage will also decrease. So generally, in case of DC shunt generator, the operation point up to this one, up to maximum load current, and full load current is somewhat below that one. Suppose this one is full load current, this one is full load current, and for this point, this gap represents all the drops, and all the drops related to armature reaction, and all brush contact drops, and all other drops. So what is given here, that all other things are to be neglected, and this one is to be considered to be an ideal thing. So what will be the voltage when load is dropped out? When load is switched off, the voltage will remain same. So voltage will remain same. If in the option there is a option that slightly increase, then that will be the answer. But here that option is not given. Only given that will remain same, increase, decrease, and become 0. And so here answer A is the correct. Remain same, because what are the conditions given? Brushes are kept in the interpolar axis and speed is maintained constant. That means brushes are kept at the interpolar axis, means this is condition for the reducing armature reaction, and here all other things are neglected, so this will be remain same. Next question is a DC shunt generator has full load voltage regulation of 10% at a rated speed of 1000 rpm. If it is now driven at 1250 rpm, then the voltage regulation of full load will be. So this will be, answer will be more than 10%. How we can analyze here? This is the external characteristic. This is the external characteristic of DC shunt generator, and what is the voltage regulation? Voltage regulation is given by E minus V by V. What is E? E is the no load voltage, V is the full load voltage, and here E minus V by V. So higher the voltage drop, here this part is the voltage drop when loaded and no load condition. This is the voltage drop, and as this will be high, voltage regulation will be high. So we know for increment of speed, suppose this one is for N1 speed and this will be for N2 speed, and here N2 is higher than N1, N2 is higher than N1. So what we are seeing, what we are observing, in case of second speed, that means the higher speed, the voltage drop, this voltage drop is higher, so as voltage drop is high, voltage regulation will be high, so this will be more than 10%. Next is, if the speed of a DC motor increases with load torque, then it is a option A series motor, option B permanent magnet motor, option C differential compound motor, and option D cumulatively compound motor. So we know that speed of a DC machine is directly proportional to EB by phi. EB is the back EMF and phi is the total flux, either that may be shunt field flux or series field flux. And here we don't know what type of machine it is, and we know that the speed is increasing with load torque. That means when load torque increases, speed is increasing. So N is directly proportional to V minus IARA. This is EB, that is EB is the back EMF by phi SH minus phi SE. If we consider the differentially compound motor, for differentially compound motor, when load torque increases, that means ISE, that is the series current will increase. Series current increases means series field flux will increase. Series field flux will increase means this will increase. This will increase means the whole term will decrease. Whole term will decrease means this is in the denominator, so N will increase. So this satisfies only for differentially compounded motor. And if we consider the cumulatively compound motor, what will happen? This will be plus, and when phi SE will increase, the whole term will increase, and this will decrease. So this is not the answer. And permanent magnet, in case of permanent magnet motor, phi permanent magnet, this is always constant, and this is not depending upon the load current. And load current is decreasing this one, and also N is decreasing, and this is also decreasing. So this is not the case. And also in case of series, this is not the case, because phi SE, in case of series, N is directly proportional to, I will write EB by phi SE. When load torque increases, load increases, this is EB is, I can represent here, V minus IARA. So when load torque increases, also IA increases, here this one also increases and this one also increases. So this whole term will decrease and this whole term will increase. So this will decrease, this will decrease. So I can write here that option C is the correct answer. Next is question number 19. A DC shunt motor is required to driven at constant power load at rated speed while drawing rated armature current, neglecting saturation and all machine losses if both terminal voltage and field current of the machine are halved. Then, so what is given here? Both terminal voltage and field current of the machine are halved. So terminal voltage is halved and field current is also halved. So now given here that n is constant, n is because this is rated speed, run at rated speed, n is constant, p is constant, p is equal to omega into t, omega is the 2 pi n by 60. This is, as n is constant, omega is also constant. So as p constant, t will be also constant, that is torque will be also constant. Now what is given? V will be halved, that is terminal voltage will be halved, field current will be halved. Field current halved means the flux will be also halved. So now n, that is the speed, is directly proportional to Eb by phi, which is directly proportional to Eb means V we will write here to be the terminal voltage by phi, neglecting IaRa. So as terminal voltage is halved and this one is also halved, this will be same ratio, that is V by phi, that is n will be same, speed will remain constant, but torque is constant. We have already defined here, torque is constant and torque is directly proportional to phi into Ia, and here phi into Ia will be constant and phi is coming to be half in the second case. So what will be the Ia will be 2, because 2 Ia should be 2 times to maintain torque constant, Ia, that is armature current, to be 2 times, that is 2 per unit. So here answer is speed remains 1 per unit, that means constant, but armature current becomes 2 per unit, that means 2 times. Option B is the correct answer. Next one is question number 20. Swinburne's method of testing of DC machine, the shunt machine is run as a, this is option A, that is motor at no load at rated speed and rated voltage. Swinburne's test is a no load test and this is not preferred for series motors, and this is the motor, the machine is run as a motor and at rated speed and rated voltage. Next question, question number 21. Question number 21. A 3-phase slip ring induction motor has 4-pole stator and 2-pole rotor. With its stator energized at 50 Hz supply, the rotor would run at a no load speed of dash. So here given that main thing is 4-pole stator and 2-pole rotor. That means stator pole and rotor pole, number of stator pole and number of rotor pole are different. So operation is not possible. So this will be at 0 RPM. So this is at 0 RPM. So we can add here that for squirrel cage induction motor, same number of pole is induced in rotor. When stator, suppose stator has 8 pole, then 8 number of poles will be induced in case of squirrel cage induction motor rotor, because in case of squirrel cage induction motor there is no physical pole structures, only the rods or the bars, conducting bars are placed. In case of slip ring induction motor, as there are windings, so we have to manually change the number of poles. So changing the number of poles in case of squirrel cage induction motor stator is easier than that of slip ring induction motor. Another thing I want to add here that if the number of phase of stator is not equal to number of phase in rotor, no problem, it will allow the operation of induction machine. But if the number of poles is not equal to number of starter poles is not equal to number of rotor poles, operation is not possible. Next question is, the MMF produced by the rotor current of a 3-phase induction motor, option A, rotates at speed of rotor in the air gap, option B, is at standstill with respect to the starter MMF, option C, rotates at slip speed with respect to starter MMF, option D, rotates at synchronous speed with respect to rotor. So here rotor produced, MMF produced by the rotor. So speed of rotor rotating magnetic field with respect to rotor structure is always S into ns. S is the slip and ns is the synchronous speed, and RMF, that is rotor rotating magnetic field speed with respect to starter structure, is always ns, that is synchronous speed. So what will be the with respect to starter rotating magnetic field? This will be 0. That means they will be synchronized, and the rotor rotating magnetic field will be standstill with respect to starter MMF. So here option B is the correct answer. Then next question is 23. Starter of a 6-pole 3-phase induction motor fed from a 3-phase 50 Hz supply which contains a pronounced 5-time harmonic. The speed of the 5th space harmonic field produced by the 5th time harmonic in the starter supply will be. So here supply is containing the 5th time harmonic. So the MMF will contain the 5th space harmonic. So what will be the speed of that one? That one will be 5 times. As this is a 5th harmonic, this will be 5 times of the synchronous speed. And what will be the synchronous speed? Synchronous speed is 120 F by P, and 120 F is 50 and P is 6. So here the synchronous speed is 1000 rpm, and as this is 5th harmonic, frequency will be 5 times. As the frequency is getting 5 times, speed will also, speed of the space harmonic produced MMF in produced MMF will be 5 into ns, that is 5000 rpm. Here option D is the correct answer. Next question is, a voltmeter gives 120 oscillations per second per minute when connected to rotor of an induction motor. The starter frequency is 50 Hz. The slip of motor is. So here a voltmeter is connected to the rotor of an induction motor, and this is giving 120 oscillations. And as this is giving 120 oscillations, so we can calculate the frequency of rotor induced EMF or rotor induced current, and that will be oscillations by time, and time is given in minutes. So what will be the per second oscillations? That is the frequency. So this will be 120 by 60. So this will be 2 Hz. 2 Hz is the frequency of rotor induced EMF. So what will be the slip? Slip is the frequency of rotor by frequency of starter. So this is the frequency of rotor by frequency of starter, that is 2 by 50, that is 4%. Option C. Next is semi-closed slots or totally enclosed slots are used in 3-phase induction motors essentially to, option A, improve starting torque, option B, increase pull out torque, option C, increase efficiency, option D, reduce magnetizing current and improve power factor. So here I will clear all the doubts from this. Now this represents a open slot. This is semi-closed slot and this is closed slot. So in case of open slot, leakage reactance or the leakage flux is low. And in case of a closed slot, leakage flux is high, because leakage flux means like this. This is leakage flux. And as there is magnetic path here, and here totally connected magnetic path, so there will be more leakage flux in case of closed, and air gap is here is more. In case of open, air gap is more and here air gap is less, and as air gap is more, to cross the air gap we have the starter will draw more current, more inductive the reactive current. So more current is drawn by the starter, and here in case of closed slots less current is drawn because air gap is less, and here also harmonic also more because air gap is non-uniform. But in case of closed slots harmonic is less due to partially uniform air gap, and in case of semi-closed everything is medium in comparison to open and closed. So here in the option directly given that to reduce magnetizing current and improve power factor. As magnetizing current increases, power factor decreases, and what is given in the question, semi-closed slots or totally closed slots. Here in case of semi-closed slot and totally closed slot, as Im decreases power factor improves, and magnetizing current decreases. So here option D is the correct answer. Next question is rotor power output of a 3-phase induction motor is 15 kilowatt and the corresponding slip is 4%. The rotor ohmic loss will be. So this is very easy thing, that is we know that the ratio of rotor input power to rotor loss to rotor output power is equal to 1 is to S is to 1 minus S. S is the slip. So here given that rotor loss by rotor output is equal to S by 1 minus S. So rotor loss will be S by 1 minus S into rotor output. So this will be 0.04. This is given 4%. 0.04 by 1 minus 0.04 into 15 kilowatt, and this is 625 watt. So answer will be option B, 625. Next question is question number 27. A starting torque of 80 Newton meter is developed in an induction motor by an auto transformer starter with a tapping of 30%. If the tapping of auto transformer is 60%, then the starting torque will be. So in this question this is given that auto transformer starting is used, and in case of tapping increase or decrease by k fraction, then torque increases or decreases by k square respectively. So as here the percentage of tapping is increasing from 30% to 60%, that means 2 times torque will be increased by 4%, that is k square. So here what is the torque? Torque is 80 Newton meter. So what will be the torque? 80 into 4, that is 320 Newton meter. And why this is happening? This is the formula. Next question is the torque angle of a synchronous machine operating from a constant voltage bus is usually defined as the space angle between option A rotor MMF wave and starter MMF wave, rotor MMF wave and resultant flux density wave, starter MMF and resultant flux density wave. Next one is starter MMF wave and the resultant MMF wave. So this is the torque angle is always resultant air gap MMF and angle between resultant air gap MMF and rotor MMF. So here I have drawn the phasors. This one E is the voltage, excitation voltage, and ER is the air gap voltage, and V is the terminal voltage. From this terminal voltage, and this is the load current, IA is the load current, and phi IA is flux due to load current, and this is this voltage drop is due to, and this is parallel to this one, this is parallel to this current, and because this is RA drop, resistance drop, and this is perpendicular to this one is perpendicular to this one, as this is reactance drop, and this is the leakage reactance drop, and this is armature reactance drop, and this both is the synchronous reactance drop. And what is lambda? Lambda is the torque angle. Torque angle is defined as E and ER, that is the resultant air gap voltage and result excitation voltage. And in this question given that MMF, so what are the MMFs? MMF here 1 MMF, that is 1 MMF here is the excitation MMF, that is phi m. I can write here Fm, this is the phi m. Another is the resultant MMF. What is the resultant MMF? One is this one and another is this one, resultant of excitation and load. This is the load current IA, load current, and this is the load flux, and its resultant is phi r. This is the resultant, and if we expand this one, suppose I will expand this one, this will be the F, that is MMF, resultant MMF, FR, resultant MMF, and always E, this phasor is perpendicular to this one, and this one ER is always perpendicular to this one, resultant. So this lambda will be reflected at this angle, lambda. So here answer is rotor MMF, and the resultant rotor MMF is the excitation MMF, and resultant flux density MMF. Resultant is the resultant of effective of FM, that is magnetizing MMF, and that is MMF produced by the load current. So there are also other angles we have to define here. I have given here. Another angle is load angle. What is load angle? Load angle is between E and V. Here E and here V. This is load angle. Another angle is internal power factor angle. What is internal power factor angle? This is the angle between excitation EMF and load current, E and IA. Next one is load power factor angle, and this is very simple. Load power factor angle is the terminal voltage, angle between terminal voltage and the load current, and the final one is a torque angle, what I have already defined. So here answer is option B. And one thing, difference between load angle and torque angle is only load angle and torque angle. This one is the load angle, this one is the torque angle. So what is the difference? Difference is the leakage reactance drop. So here is the answer. Next question number 29. Curves X and Y in the following figure denotes open circuit and full load zero power factor characteristic of a synchronous generator. Q is the point on ZPF characteristic at 1 per unit voltage. The vertical distance PQ in the figure gives the voltage drop across. So here in this given figure, X is the here given X and Y is the following figure denotes the open circuit and full load ZPF. This one is the open circuit OCC, and this one is the ZPF. So PQ, what is PQ? Question is asking for PQ. So PQ is the voltage drop due to synchronous reactance. What is a synchronous reactance? Synchronous reactance is the part of synchronous impedance. ZS is equal to RA plus J into XS, and XS is equal to XL plus XA. This is leakage reactance, and this is armature reaction reactance. So this is this one. So this is not in options given that synchronous reactance. This is actually voltage drop due to synchronous reactance. So here option A is correct, but language it is not correct. Language should be voltage drop due to synchronous reactance, because the y-axis here is in volt, y-axis is in volt, x-axis is in current. So this will be in volt. Next question is xd, xd prime, xd double prime are steady state d-axis synchronous reactance, transient d-axis reactance and sub-transient d-axis reactance of a synchronous machine respectively. Which of the following statement is true? Which of the following statement is true? So here option A is correct, because this one is greater and then this one and then this one. Next question, here a field excitation of 20 ampere in a certain alternator results in a armature current of 400 ampere in short circuit, 400 ampere in short circuit and a terminal voltage of 2000 volt on open circuit. The magnitude of internal voltage drop within the machine at a load current of 200 ampere is. So here given that a field excitation of 20 ampere in a certain alternator results in a armature current of 400 ampere in short circuit and 2000 volt in open circuit. So here I have drawn the OCC and SCC, that means open circuit characteristic and short circuit characteristic of synchronous machine. And here what we are getting, suppose this one is 20 ampere, this one is 20 ampere. For this 20 ampere I am getting SCC, that means short circuit current of 400 ampere and 2000 volt for OCC, open circuit voltage. So ZS, that is the synchronous impedance, will be OC voltage by SC current at constant field current. So this will be 2000 by 400, which is equal to 5 ohm, So what, this is the mod, this is the magnitude, and what will be the internal voltage drop at 200 load current? So load current voltage will be I into ZS, IL by ZS, IA by ZS. IA is the armature current into ZS. So this will be 200, given 200 into 5, this is 1000. 200 into 5, this is 1000. Here option D is the correct answer. Next question, question number 32. The angle delta in the swing equation of a synchronous generator is this is actually the angle between rotor axis and the synchronous rotating axis. Rotor axis and the synchronous, which option is correct? Option D. Option D is the correct answer. Angular displacement, an axis fixed to rotor with respect to a synchronously rotating axis. That means the stator rotating magnetic field is the synchronous rotating axis. We have to make one axis to the synchronous rotating field and another to the rotor, and this should be ideally in synchronized manner. That means the delta should be 0 ideally. When a load is connected, delta will lag, the rotor will lag to the stator rotating MMF field or the synchronous rotating field. And if load is removed suddenly, rotor will lead, and this will be stabilized after some fraction or after some swings. That is why this is called swing equation. So this is the answer here, option D. Next question, question number 33. An alternator has full load regulation of 4% when the power factor load is 0.8 lagging while alternator runs at 1500 rpm. The full load regulation at 1400 rpm of 0.8 power factor lagging load will be. So in case of alternator, voltage regulation does not depend upon the speed, because in case of alternator changing of speed is not possible. So this will be remain constant, that means 4%. Next one is 33. Next one is 34. A synchronous motor is running at a leading power factor. Its excitation induced voltage EF is. So here given that leading power factor, synchronous motor means this is a load, and load is leading means Q is negative. Load is leading means Q is negative, P minus JQ. This is leading load, just like capacitor. Leading load, Q is negative, and we know that reactive power in case of a synchronous motor is given Q is equal to V by Xs into V minus E cos delta. So as Q is negative, this one is negative, means this term is high. This term is high means option B is correct. Option induced EMF EF is higher than terminal voltage. EF is greater than terminal voltage. Next question number 35. Question number, this one is question number 34. Where is 35? This one is 33, 34. Yes, this is 35. In a salient pole synchronous motor, the developed reluctance torque attains the maximum value when the load angle is in electrical degree is. So we know that torque is equal to power by omega, P by omega. So power developed in case of a synchronous motor is equal to EV by XT sin delta plus V square by 2 into 1 minus XQ minus 1 minus XT into sin 2 delta. So this is in case of salient pole synchronous motor. So first part is called the electromagnetic power, and in case of cylindrical rotor only this part is present, but in case of salient pole motor this part is present. And what is this part? This part is reluctance power, and due to this part salient pole generator are more stable than that of cylindrical machines. So this is the reluctance power, and reluctance torque will be derived from this one. This power by omega will be reluctance torque, and this is depending upon sin 2 delta. Then when this whole term will be highest when sin 2 delta will be 1, because sin has a value from -1 to +1. So when will be sin 1, this will be 2 delta will be 90 degree and delta will be 45 degree. When delta will be 45 degree, this will be high. So reluctance torque will be high. Reluctance torque attains the maximum value at 45 degree. Load angle of 45 degree. Next question is question number 36. Question number 36 is given that a 3-phase synchronous motor connected to AC mains is running at full load and unity power factor. If its shaft load is reduced by half with field current constant, its new power factor will be. So given that 3-phase synchronous motor connected to AC mains is running at full load and unity power factor. If its shaft load is reduced by half, so here what is given? Shaft load is reduced to half, that means P is reduced, and here E, V and Xs are kept constant, and as P is reduced, sin delta is to be reduced. Sin delta is to be reduced means delta is to be reduced. So final we are getting that delta is to be reduced, and we will draw the phasor and we will find what is the effect of this one. So here is the phasor I have already done. So here suppose this one is V, this one is the V is the reference here. So current is fast, given that unity power factor, fast is unity power factor, load and unity power factor, running at unity power factor. So current will be in phase. So as this one is V, current is in phase I1, current is in phase I1, first case current is in phase. So what will be the E1? E1 is the excitation EMF. What is the excitation EMF? And the excitation EMF is the terminal voltage plus the voltage drop due to synchronous reactance, and this is the synchronous reactance drop, and voltage this one E1 is the E1 is the excitation EMF. And second case, when delta, this one is delta 1, and what we are getting, delta 1 is decreasing, that means this angle is decreasing. So we have to put here E2, here this one is E2, this one is the second case where E2, this is the second excitation voltage, and for this corresponding I2 will be like this, corresponding I2 will be like this, I2 will be like this, because this is perpendicular to this one, this is perpendicular to this one, so I2 will be like this. And what we are getting, phi is, this one is again leading, this one is in phase when this was unity power factor, now this one is leading, phi is positive, and so this one is leading. Next question, question number 37. Two alternators A and B are sharing an inductive load equally. If the excitation of alternator A is increased, excitation of alternator A is increased, so what will happen? Here are the options. So here A is 1 and another is B, two alternators, and when excitation of A is increased, kilowatt, that means real power shared by A and B will be same, kilowatt, that means watt power active power will be same, but the reactive power of A will increase, whereas as this one excitation is increased, reactive power provided by A will increase, whereas this will decrease, So now kVA will increase, this is apparent power, and this will increase because kVA reactive power is increasing. As reactive power is increasing, this will give you more current. Reactive power production is increasing in case of A, as the result of excitation increment, IA, that is the armature current, will increase, and in case of B this will decrease. So here as armature current is increasing, power factor will decrease, and here power factor will increase. So here what is the conclusion? Alternator B will deliver less current, alternator B will deliver less current, alternator A will deliver more current. So if the alternator A excitation is increased, then its current will increase. The alternator whose excitation increases, the same alternator will have experienced the more current, will deliver more current, but the real power sharing will be same, reactive power sharing will be different, and maximum reactive power will be observed for the increased excitation machine. Next question is, consider the following single phase motors: capacitor start motor, capacitor start and run motor, permanent split capacitor motor, shaded pole motor. The correct sequence of the increasing order of their cost. So here this one is the most costliest, then permanent split phase, and then this one, and then this one. So here option is this, increasing of their cost, so sorry, this one is the cheapest is this one, because in this case no capacitor is used, in this case special capacitors are used, of high capacity, and in case of somewhat low cheaper capacitors are used. Next question is question number 39. A 1.8 degree step 4-phase stepper motor has a total of 40 teeth on 8 pole of starter. The number of starter teeth for this motor will be. So here step angle is equal to, step angle here given that 1.8 degree. So step angle formula is 360 by m into nr. nr is the number of rotor teeth, m is the number of phase. So here 360 by m into nr. nr is the number of rotor teeth. So what will be nr? nr will be 360 by m into step angle. Step angle is beta. So this will be 360 by m beta. 360 by 4 into 1.8 degree, which is equal to 50 number of rotor teeth. 50 number of rotor teeth. So the next question is question number 40. In a step motor, the detent torque means. So what is the detent torque? Detent torque definition is maximum of static torque with the phase winding unexcited. This is the definition. Option D. Option D is the correct answer.